From afar, Earth appears calm, blue, and peaceful. But this peace is nothing more than a thin shell resting atop a massive machine that never stops moving. Just beneath this crust, enormous plates are slowly but constantly shifting, and sometimes these movements reach a point where the energy released in an instant can destroy cities and shake entire continents. So how does such immense power emerge? And why are some earthquakes barely felt, while others can affect the whole planet? To understand this, we need to look at Earth's structure. The crust is not a single solid surface, it's divided into giant slabs, much like pieces of a jigsaw puzzle. These tectonic plates float atop the semi-fluid mantle beneath them. Although plates move only a few centimeters per year, these tiny shifts involve masses of millions of tons, creating enormous energy buildup over time. When plates converge, diverge, or slide past one another, fault lines form along their boundaries. But these faults are rough, and the plates cannot easily glide past each other. Instead, stress slowly accumulates. It's like a spring stretching closer and closer to its breaking point. And when that critical threshold is reached, the fault ruptures suddenly. The energy released in that instant radiates outward as seismic waves. The power, or magnitude, of an earthquake depends on the amount of energy released. Today, scientists most often use the moment magnitude scale, MW, to measure it. On this scale, each whole number increase represents about 32 times more energy released. This means a magnitude 9.0 earthquake releases 32 times the energy of a magnitude 8.0 quake, an almost incomprehensible difference. Throughout history, humanity has witnessed the devastating effects of such immense forces. In 1960, the Valdivia earthquake in Chile, Magna 9.5, became the most powerful ever recorded. The energy was so great that it shifted Earth's axis by millimeters. The resulting tsunami traveled across the Pacific, reaching as far as Japan. In 2004, the Indian Ocean earthquake, 9.1 to 9.3, generated a massive tsunami that struck 14 countries, killing over 230,000 people. The waves were so powerful they continued hitting coastlines for hours. In 2011, Japan's Tohoku earthquake, MW 9.0, unleashed towering tsunami waves and triggered the Fukushima nuclear disaster. Entire stretches of coastline receded before walls of water crashed inland. The 1906 San Francisco earthquake, Maru 7.9, left the city in ruins, not only from the shaking, but from fires that burned for days. And in 2010, the Haiti earthquake, a 7.0, became one of the deadliest humanitarian crises of modern times due to the country's lack of resilient infrastructure. Earthquake waves fall into three main categories. P waves, primary, the fastest, usually the first to be detected. S waves, secondary, slower, but cause stronger shaking. Surface waves, the most destructive, responsible for the heaviest damage to buildings and infrastructure. Scientists cannot yet predict the exact time of an earthquake, but by studying stress accumulation along faults, seismic activity, and historical records, they can identify high-risk areas. Early warning systems in countries like Japan, Chile, and the US sometimes provide only a few seconds of notice, but in a quake, even seconds can save lives. Major earthquakes are part of Earth's natural cycle. We cannot stop them, but through science, we can understand them and reduce their impact. With resilient buildings, informed communities, and sound engineering, we can create a future better prepared for these powerful natural events. Because it's not the earthquake that kills, it's the lack of preparedness.